I did edit it. You can look at the video. I did edit it out, so you're safe. Um, all right. So let's take a look at this. Hopefully, a fairly quick review into kind of what we were looking at the other day. So evaluating limits. In this case, same function, looking for the limit as x is approaching 2, as well as the limit as x is approaching -1. What was our methodology when we had an equation like this in order to figure out what the limit would be around these values?
Again, the number around
like yeah, plug in values that are really close, but not exactly the same as the value that we are aiming for, and seeing, is there a trend to what we see? So we don't really know, nor do we particularly care what's actually going on at 2. We're saying what goes on around 2. So what did you guys plug in to test? What did you do to figure out what's going on to the left? 1.9 and 1.99, just getting increasingly close. So we'll do our left-hand limit here. This would be 1.9 squared plus 7 times 1.9 plus 6 over 1.9 plus 1. I get 7.9. And when I do the same thing, but I get a little bit closer, so we'll do 1.99 instead of 1.9. 99. We get even closer, what appears to be the value that we are converging to. It appears to be 8. And so we might say something like the limit as x is approaching 2 from the left of this particular function is 8. Okay. Same idea, but we can't just check the left. We also have to check the right. What are the values to the right of 2 that we could plug in just to get a feel for what's going on? Like 2.1, 2.01. Sure, seems good. So we'll just replace everywhere that we got this with a 2.1. Very riveting stuff. Okay, we get 8.1 over here, and then I'll leave as a bit of an exercise to the reader. This is 8.01. What does seem to be the limit as we are approaching from the right? Also seems to be 8. Oh, no, the limit as we approach 2 from the right of f of x also seems to be 8. Do they agree? Yes, indeed they do. So 8 certainly does agree with 8. And so the limit here exists and is 8. Yeah, Chris.
Why do you do all that if we could just plug into?
Put a pin in that idea. But your observation that limits are probably overkill in this case is correct, and we're going to look at that here in just a second. But put a pin in that question. Yeah. And when you plug in 2, you notice you get exactly the thing that the limit is telling us that we're going to get, which is not a coincidence. But the TLDR is try to do the same thing with the next one, and you will realize that, oh, well, I can't do the same thing. Okay, so exact same idea here. I'm gonna shortcut this a little bit, plugging in the values that are around -1. So this should be to the left would be like -1.1, -1.01. I think you get what, like 4.9 and 4.99. And then to the right, -0.99, -0.9. I get like 5.01 and 5.1. What appears to be the limit here? A limit feels like it's going to be 5. Sorry. Okay, questions with the admittedly very overkill, and we'll see not very necessary process by which we, at least in this case. Plugging values around. Do we actually care what's going on at 2 or -1 for these questions? No, that is completely irrelevant to us. It does not matter. We are asking the question what's happening as we're getting really, really close. We actually completely ignore what is going on at the exact value. Sometimes because we can't look, sometimes because we can and it matches, and in either case we don't care. It's just a different function. Okay, so Cruz asked a really good question here, which is why did we need to do this for example? With example 1 in particular, with example A here, we can actually just plug the value of 2 into our function and figure out what's going on. And what Cruz is kind of hinting at, what he's kind of pointing at here, is the idea that most of the time, I would say like 99.9% of cases, the limit and what the function is actually doing are going to get. And most of the time you can get a thing that's like, oh, well, the limit and the function agree if the function is continuous, and then, oh, the function is continuous if the limit and the thing agree. And it's like this gross, like circular thing. So I'm going to try and avoid doing that. What I'm going to say instead is most of the time we are going to see some kind of agreement, but there are some situations in which the limit is better equipped to handle what is going on. But wouldn't it be lovely for our limit purposes if we didn't have to do this process every single time? Wouldn't it be awesome if we could just plug the value that we are asking about into the function and see what's going on? And the answer is yes. And then the answer is, so let's do that. So we are going to be looking at a couple of analytic techniques. So not just brute force going through our calculator and figuring out, just randomly plugging things in and seeing what's going on. This is like algebraically, how do we compute the limit in a way that doesn't require us to like plug in 8 different values into our calculator and, hope that we guessed correctly. And the principal one that you're going to use in the vast majority of cases, although we will see that not every function, in fact, some of the functions that we have already looked at do not play particularly nicely with this, is going to be direct substitution. If we can, we're going to try to do direct substitution. So a couple of conditions for direct substitution. There are some situations in which direct substitution always works. And then even in the cases where it sometimes doesn't work, there are still times where it does. So it's a very powerful tool. And in fact, those edge cases where it doesn't necessarily work, but sometimes does, is actually when limits are at their most powerful. That's when it is the most useful to talk about limits. So if, normally here you would say if our function is continuous. I'm going to try to avoid that word until our next lesson. So if we have no domain issues, or our function is not piecewise, around the value a, then we can find the limit by simply plugging the value into the function. The limit as x approaches a of f of x is just equal to what we get when we substitute a in for x. So a couple of things that I want to highlight about this definition. First and foremost is this around a. My function could be a gross piecewise mess. Right? We could think back to maybe the example that we looked at here. This function is a gross piecewise mess that has some domain stuff going on, some like missing values and whatnot. But if I zoom in at what's going on at -2, do I have any weirdness that's going on with my function if I'm just looking about what's going on around -2? No, and so I can kind of ignore all of the weirdness that's going around everywhere else and just treat this like it is the function that we have going around at -2, plug -2 and see what we have going on. Okay, so that's the first thing to kind of note, is that if our function is being well behaved, no domain issues in the kind of vicinity, no piecewiseness in that region, then we can just use direct substitution. That's really nice. But what's really, really powerful, yes. Yeah, go for it. What's really, really powerful here is that these conditions of when we don't have domain issues, when we are not piecewise, that doesn't mean we can't do direct substitution. It just means we need to be careful in doing direct substitution. So I'm going to put asterisks over the no domain issues and the not piecewise. Because if we don't have domain issue, or if we do have domain issues, if there are domain issues, then if we can simplify, so if simplification removes domain issues, then we can do direct substitution anyway. And if the function is piecewise, then we'll refer to example 2. We'll look at what happens when that is the case. Okay. So let's look at the bell work. Let's try this in the context of the bell work to see what I'm talking about, to see why limits are a really cool tool and why these things are worth talking about at all. Let's consider A here, which Cruz noted, this is an example where why can't we just plug the value into our function and see what we get. Okay, so let's focus on, can we use direct substitution here? Is this a good candidate for direct substitution? Do we have, for this function, any issues with our domain? What could cause domain issues? Two things. Dividing by 0 or square roots of negatives. The main one we're going to look at is dividing by 0. I don't think there are resolvable domain issues for square roots of negatives. I could be wrong. So dividing by 0. Do I have to worry about dividing by 0? Why?
You're gonna add one.
Okay, so around 2, I certainly do not. In general, do I? Yes, we'll look at B here, and that'll be for B. But for when I'm looking at an x value of 2 and x values that are around 2, I do not have to worry about dividing by 0, which means near 2, my domain is good. We're good to go. And so we can just do direct substitution, in which we are simply plugging in our 2 into our value of x. This is going to be 4 plus 14 plus 6 divided by 3, which gives me 24 over 3. That is 8. Which matches the limit that we had already found. Obviously not a coincidence. Those two are the same. Okay, direct substitution really, really works well here because we don't even have to worry about anything. We're not running into domain issues. We can just go ahead and plug in and see what's going on. So that's the easiest case. Slightly trickier, though, is what we see with B. Do I have any domain issues around -1? Yes, what's going on when x is equal to -1? I'm dividing by 0. Okay, so if algebraically we are not able to get some kind of cancellation to go on here that eliminates this x plus 1 from our denominator, then direct substitution is going to be a no-go. We're going to have to fall back on this table. But if I can get that x plus 1 to cancel, then we can do direct substitution anyway. So let's see if we can't get this x plus 1 to cancel. How could I factor in my numerator x squared plus 7x plus 6? x plus 6 times x plus 1 all over x plus 1. And what's going to happen here? The x plus 1s are going to cancel. And we are just going to be left with x plus 6. Do I have any issues with plugging -1 into x plus 6? No, I do not. And so I will go ahead and do my direct substitution with my simplified version, this x plus 6, to get -1 plus 6, which is in fact equal to the 5 that we found from our table. This is, you'll notice, exactly the same thing that we did when we were looking for holes. Now, though, we have language to put to it. Now we're talking in the context of limits, which kind of, again, gets to that idea of we don't actually care about what's going on at -1. We just care about what our function should be doing if it were allowed to reach negative. Okay. So a very, very powerful tool. This is when it's at its most powerful, which is going to be for figuring out what is going on when I would normally be dividing by 0. Otherwise, it's like, why is this a new thing? It's overkill. But when it is not overkill, is this case specifically when we have some kind of cancellation. Super, super important idea, by the way. This is what's going to let us like take derivatives. So this is like, if there's one thing that is like the most important thing, it is probably this. Questions with our direct substitution examples with the Bellerkin? And there are a ton of these on the classwork. So if you're like, oh, this is fine, I just want to practice, those are going to be really, really, really good examples for you guys to run through. How's this feeling so far? No, there's a Pearson. Yeah. 18. Yeah, and a lot of them are just like, or like some of them. A lot of them are direct substitution, which is just like plug in. It's pretty straightforward. The ones that are like that are like, look at the graph. Yeah. Like there are some look at the graph ones that are like a bunch of subparts, but like you're looking at a graph, so even that should take like a minute. No. Okay, so we see that direct substitution is a really good tool to get around this sometimes dividing by 0. I will say it is not a ubiquitous tool. It doesn't always work. Great examples of when it doesn't always work are basically every single example that we looked at on Friday. You would not be able to approach these with direct substitution. I actually will say someone in second period, when we were first solving these, did figure out a way to do direct substitution on A, which was kind of cool. They did difference of 2 squares to factor x minus 9 into the square root of x minus 3 times the square root of x plus 3, and then we got some cancellation stuff. I would not expect you to do this. I would expect the table from something like this. There are other ways as well to kind of handle these. But like, for instance, sine of x over x, how are we supposed to handle that without the table? There's nothing that's going to cancel the x. We're completely at a loss for that. And frankly, every single one of these, except maybe the absolute value of x over x, we don't have a way to actually handle them. We don't have a way to get any direct substitution going. That is when the table method becomes very, very useful. It'll always work. Just a quick heads up. You can always construct a table, and that will always 100% get you the right answer. So if you're waffling between like, oh, I'm going to just try to do one technique all the time, that is the technique to do. It's just a little bit of a waste of time when we have cases like this where you can just plug in 2 and see what's going on. And we'll see it makes derivatives terrible. So we're going to try and get that locked down. Okay, so let's actually look quickly. I'm skipping example 1 for now. Let's take a look at example 2. And I want to take a look at how direct substitution can help us with our piecewise function. So in this case, we have the limit as x approaches 3 of f of x. F of x is piecewise. We have one definition for things that are to the left of 3, one definition of things that are to the right of 3. Quick thing to note, if this was just like 4 and it wasn't kind of at that break, you could just plug 4 into the function. You can just do direct substitution right away. Easy, no worries at all. Totally fine there. Right. But in this case, because we fall kind of on the edge here, we need to take into account kind of our definition of limits, essentially. So just kind of a reminder, a little bit of a good, helpful piece for people who weren't here on Friday. What did we need to do to demonstrate that the limit overall, that the limit as x approaches 3 overall exists, and then also to figure out what it is? To the overall limit. What did we need to show to demonstrate that that overall limit exists?
The left side equals the right.
The left side limit and the right side limit have to be in order for us to be able to say that the limit overall exists. So let's take a look at example 2 here and see what that is saying. So if we are trying to figure out what is going on as x is approaching 3, that is really 2 questions. We have to ask the question, what happens as we approach 3? Okay. What happens as we approach 3 from the left? And we ask what happens as we approach 3 from the right. Okay. If I am to the left of 3 and moving in towards 3, which definition for my function should I use? Should I use my top equation for values that are less than 3, or should I use my bottom equation? We're going to use the top equation, right? Less than 3 means that I am using my 2x plus 1 version. So this is the same as the limit as x approaches 3 from the left of 2x plus 1. Do I have any domain issues with 2x plus 1? Nope. So what do I get to do? Yeah, let's just plug 3 in, see what we get. And what do we get when we plug 3 in? That's just 7. Cool. Okay. What about when we are approaching 3 from the right? Which definition are we going to use? We'll use the bottom definition here since we are approaching from the right. So this is the limit as x approaches 3 from the right of x squared minus 2. Do I have any domain issues with x squared minus 2? No, I do not. So what do I get to do? Just plug in, and what do we get? 7. So do my limits agree? Yes, they do. 7 is in fact equal to 7. And so what is my overall limit? 7. Cool. Let's try the exact same thing for B here. So we need to figure out the left-hand limit as we approach 4. If I'm talking about the left-hand limit, which equation am I going to use? Use the top one since we're talking about the left-hand limit. We need to use when we are less than 4. So the square root of 2x plus 1. Do I have any domain issues around 4 if I'm looking at the square root of 2x plus 1? Around 4? No, not around 4. Certainly somewhere, right? Certainly x gets negative enough. I'm going to run into domain issues. Not around 4, though. And so what is my direct substitution telling me this limit is going to be? That is going to be 3. And let's check to the right as well. Okay. Which equation am I going to use if I'm looking to the right? I'll use the bottom equation here. Do I have any domain issues with just x? What does direct substitution then tell me? 4. Do my left hand and right hand agree? No, they do not. And so what is my overall limit? Does not exist. The limit does not exist. Which as we'll look at on, as we'll look at when we do continuity, that means that the function is not continuous in that way. Okay, how does direct substitution feel? Pretty, hopefully pretty straightforward. Questions, comments, concerns? Okay, we'll be back. I want to continue on, but yeah, we'll go back. Okay. One other thing to talk about when we are looking at kind of some of the analytic properties here of our limits is going to be that they behave really, really nice. Which is, kind of good news for us. We like it when the things do what we expect them to do. Essentially, we are going to be able to treat our limits kind of like the pointwise operations that we saw earlier, where we're really going to just evaluate each of the limits individually rather than generating a brand new function here. There is definitely a more precise way. I'm going to try and communicate this information without listing like 8 different rules. If you look in a textbook, they list out like 8 different rules here. I'm going to try and condense those to like 2, and then just an understanding that you'll be able to figure it out from there. So let's see here. We have the limit as x approaches a of f of x. Okay, here's where we get a little jargony. I'm going to use what is called, actually don't know if this has a name, I'm sure it does. I'm using this symbol as a generic operator. Which is just to say that could be addition, that could be subtraction, that could be multiplication, that could be division, it could be exponentiation, anything that we would expect some kind of way to combine this function with another, it can do any of those, right? Which is just to say I don't want to write a separate rule for addition, subtraction, multiplication, and division that all say the same thing. So I'm not going to. I'm going to use my generic operator. And the way we handle this, rather than just generating a new function and figuring out what's going on here, we're going to kind of distribute the limit, but I don't like that because the limit is in and of itself an operation. So we're not really doing distribution here. We're really abusing the fact that the limit is a linear operator, but that's fine. You can kind of think of it as distribution if you want to hurt my soul. The limit of f of x, and then whatever operation we're doing with the limit of g of x. You can kind of distribute them, but don't call it distribution or I will haunt you for what we have going. I'm pretty sure this is an example of linear operators. I guess I'm second guessing myself now, but I'm pretty sure this is not distribution and this is linearity. Okay. So we have that. And then we also, another kind of example of like things that we can do. Essentially, you can just, the PEMDAS here doesn't really matter. You can do limits first. You can do the limits last. It doesn't matter. For instance, if we had the limit as x approaches a of c times f of x, we don't actually have to multiply by c first. We could bring the c out and multiply it after we take the limit as well. Order here doesn't really matter. And because order here doesn't really matter, generally speaking, we take the limit first and then we figure out what's going on. Then we do all the fancy like changes and whatnot. Okay. That feels like a lot more than it actually is. Let's look at an example. And basically the translation is going to do what you want it, which keeps it. Okay, so let's take a look here at, let's take a look here at A. If you let x approaches -2 of minus x, given these definitions for H and G, which using algebraic properties, this is overkill. You should not do this when answering this question, but just to demonstrate be the same as 3 times whatever the limit is as x approaches -2 for h of x minus whatever the limit is as x approaches -2 for g of x. Again, that is overkill. I do not actually want you doing that for every single one of these problems. This is more demonstrative than anything else. And then we look at our graphs here. What is the limit as x approaches -2 for h of x? Yep, we approach from the left and we approach from the right, and they agree, and it is -1. So this is 3 times -1. And what is the limit as we approach -2 for g of x? It is indeed 5. Approach from the left, approach from the right. They agree, and they agree on 5. And so this overall limit is -8. They do the things you would expect them to do. Sure. Find the limits first and then just plug them in as numbers. Okay. Questions with the algebraic stuff? All right, take a minute. Take a stab at A, or sorry, B, C, and D.
Oh,
yeah, I forgot.
I forgot DB.
Wait till the next one's on the left. Look at that. It wasn't that.
Little bit sick. It's funny.
It wasn't that bad. Just going.
Sorry.
Sorry, yes, yeah.
So,
And listening days each of 1 is 3 Yeah,
So
but
you
not
put in
it would be 3 times.
It's like 3 weeks.
Is it the bad guy?
It takes forever because all the cardinals have to write down a name. It's very shit.
Yeah.
If it's wrong, they throw it in chip. Yeah, if it's wrong, they throw it in chip.
Did you see the video?
Process.
What's
Because
his
we're
name?
approaching.
Yeah.
so we're
Oh,
approaching
we're getting
to
gray.
some question.
It was some YouTuber. He's in the famous.
Okay.
It's not Children's.
Yeah, you're gonna assume that it's gonna be.
Children's from the
Yeah.
There are instances in which historically that
I think that's
has
a great idea. Children's.
that has messed us up. But it's a fair enough assumption, and we don't at the moment have the tools to be able to
That's
tap
so
that's being shipped.
that's good.
Yeah.
It's been for like a couple of years.
So just get every
Ran for Pope.
Yeah, right now it's a little bit vibe space, but that's okay.
I think it would be perfect for like.
And you have to be Catholic.
I could run for
And you
Pope.
gotta become a priest.
Have you seen
And then
the
you-
CGP Perry video?
Yeah, that's what we were.
That's what we were talking, yeah, you gotta become a priest.
Which is so wild because I saw that when it came out.
For-
Yeah, 12 years ago when it released.
The
I,
first time on Friday.
Yeah.
I saw it the first time like
Yeah.
Thursday.
no, that was like one of his like early days, like short form videos, which are incredible and he's absolutely incredible. But no, like I saw that back in like middle school. I guess that would have been, that would have been.
Was that like when he first
Well, I
got
think you go to,
like
like,
inaugurated?
the-
The
No, it had nothing to do with anything, it was just training.
Oh.
It was just like, it's funny, it's this is the very first time that video has been.
Because I didn't even think
Yeah.
that. That's the answer to the question that I asked him. You gotta go to.
what's your opinions on Trump becoming the new pope?
I'm not gonna answer that question.
I saw that, that's funny.
Hell, that's AI and the whole.
That was hilarious. Like 5 years.
Sorry.
Well, you have to be, so you don't have to, technically, the only 2 requirements are, well, you've seen the video, are being a man, being a Catholic.
Yeah.
But they are effectively more.
He only needs. What is it?
Yeah, Cardinals aren't gonna select it, it's not black.
But you gotta be.
What would happen if Trump converted to being Catholic, became the Pope, and then converted back to
Gets
Christianity?
everybody to vote for him. I'd vote for him just for shits and
Yes,
gigs. I think Christian, I'll vote for him.
You have to become a priest, then you have to become a
Second
bishop,
term.
then you have to be anointed by a cardinal
No,
to be a cardinal.
Bishop is
would
higher
they-
than priest.
Yeah.
It takes like months.
And then.
You have to get like a PhD.
You have to. Yeah.
Yeah.
PhD in,
Yeah, to become a bishop, you need a PhD in like theology. Yeah. Yeah.
And then you have to get all the cardinals to vote you. And
So probably like the hardest job in the world to get there.
It is,
then if the Pope specifically.
yes.
wrote-
Well, there's only one pope out of 8 billion people, so. It is harder to become name any job than the job that only has one person who is doing it. Okay, let's take a look. Let's take a look here at what we've got. What did we find for our limits for H and G as we were approaching 1? 3 and 3? Agree? And so when I take the product of these 2 functions and the limit of that product, what are we going to get? 9. When I take the quotient of these 2, what are we going to get? 1. And then what did we find for the, so this would be the square root of the limit as x approaches 2 of g of x. What did we find for this? Yeah, square root of 4, which is 2. Perfect. Okay, limits behave well. Good to know. All right, 2 more examples that I'm going to add because they are fun and interesting. Yes. So the limit as g approaches positive 2. So what's the y value that we are approaching? We are approaching 4, but then we're taking the square root of that, so 2. Yeah. Okay, so we are going to take a look at 2 fun examples here. which is that composition makes this complicated. For a couple of reasons. But the big thing that we are going to really need to do is direction. That is going to be the kicker for determining are we even able to do this at all. Is that the direction in which we are doing the approach becomes very critical. So let's take a look at what I mean by considering E here. This is the limit as x approaches 1 of h of g of x. Just a quick reminder about composition. How would I go about figuring out what is going on here? What does h of g of x even mean? Is it multiplication?
Oh, no, plugging it into the.
Okay, so we're taking the output of g and we're using it as an input for h. So we first need to figure out, okay, what is g doing as x is approaching 1? And then the question is, okay, how is h going to respond? Maybe another way to think about this is this would be, this would be like h of the limit as well. Even that's not quite true. So that's fine. We'll just take these each individually. The first thing that we need to focus on is what is the limit as x approaches 1 of g of x. And then we'll apply it to what we see here for h. Okay, so as we are approaching 1 for g of x, what is the output that we are getting closer and closer to? 3. Okay. And so this limit would be equivalent to, we're saying our outputs, the things that we are plugging in to our value, to our function h, are getting closer and closer and closer to 3, right? As we get closer and closer to 1, h's input gets closer and closer to 3. This is the same as the limit as x approaches 3 of h of x. Okay. Here's the hard bit. It matters how we are approaching this value. This gets to be a little bit tricky. For instance, we could think about the outputs of g as being what I'm plugging into my function h. So as I approach 3 from my left-hand side, what is true about all of these numbers that I'm plugging into h if I'm approaching in the way that I'm approaching? What are their values going to be relative to? Closer, I'm getting closer, I'm getting closer. What kinds of values is h as I approach from the left? So as I'm getting close to 1, I'm looking at the outputs. What's happening to the outputs? Right, so we're getting close to 3. What's an example of an output that I would see as I come in from the left? 2. Okay, important here. Why did you say 2.9 instead of like 3.1?
It's coming from the left and that's before it.
Because we are coming up from below this particular point, right? We are increasing towards 3 rather than decreasing towards 3. So from the left, we're getting like 2.9, 2.99, 2.9999, whatever, getting close to 3. Whereas from the right, what kind of outputs are we seeing? 3.00001 values that are really close to 3, but above 3. And so we are approaching 3 from both directions. We're approaching it from below, we're approaching it from above. As a result, this is a two-sided limit. So because we are approaching from above and below, this is two-sided. And so we ask the question, what is the limit as we approach 3? When we ask that question, what do we actually need to check? When we're taking an overall limit, what do we actually do? We theoretically could do that. If we had a function, we would do that, but you're kind of getting close to that. To find the overall limit, what do I need to look at? Not the origin, but left and right hand. Do the left hand limits and the right hand limits agree? In this particular case, what is the limit as I approach 3 from the left for h of x? It is 1. So as we approach from the left, my limit is 1. And what is the limit as x approaches 3 from the right for h of x? Say again. 5. And so what can I say overall? Do my limits agree? Therefore, limit does not exist. So we used g of x first because it's composition, right? First, we use g of x to determine what is the actual value that we are approaching. What is our input actually getting close to? And we said, okay, if I'm approaching 1 from the left, I'm going to be approaching 3 from below. And if I'm approaching 1 from the right, I'm approaching 3 from above. Okay. So the fact that it's above and below means I'm looking at two sides, right? I'm approaching 3 from both directions. And overall, I'm approaching 3. So this input is getting closer and closer and closer to 3. Another way to say that is that the limit is x approaching 3 of h. It's like how we communicate that. Let's run the exact same thing, but let's reverse the composition. And let's see if these are going to stay the same, if something's going to change, so on. Okay. In this case, we're looking at the limit as x approaches 1 of g of h of x rather than h of g of x. So what is the first thing that we have to do for this kind of composition? What would you guys do first? We are going to need to figure that out. That is certainly something that we're going to need to factor in. When I am talking about this limit, which function am I looking at first? Am I first looking at h or am I first looking at g? First, we're looking at h. Okay, so the first thing we need to establish is what is the limit as x approaches 1 for h of x? Okay, it is 3. What, though, is different about this 3? Well, it's always going to approach like left and right. But then what do we notice about the outputs that we are going to see? They are greater than, less than 3. I'm getting closer and closer and closer to 3. Am I saying things like 3.1? Am I saying things like 3.0001? No, we are only seeing outputs like 2.9, 2.99, 2.9999999. Even though we are trying to take a two-handed limit, two-sided limit, we are not actually being able to achieve that because regardless of which direction I'm approaching 1 from, I'm approaching from below. And as a result, everything that I can plug into G, if you think about like constructing the table here, all of those are going to be a little bit less than 3. Therefore, this is a left-handed limit for G of x. Again, the idea is that because we are only approaching 3 from below, this is a left-sided limit. Yeah, go for it. And so what is our left-handed limit as we are approaching G from the left, as we're approaching rather 3 from the left? from the left. So start to the left and move inwards. 5. Even though it doesn't agree with what's going on the right, that's fine. We never see 3.1. We never see 3.00001. We're not even approaching this value from this. Those are a little bit tricky. We'll do some more practice. A little bit later. Questions with our example 1 here? Compositions, probably a little bit tricky. It's just like one extra thing to check for is, are you approaching above and below, or you're approaching double above, or you're approaching double below? But it is one extra thing to check for, and so it's certainly a little bit tricky. Any questions? Okay. Let us then okay, one more thing that we're going to look at today. It's going to feel a little bit complicated. I promise it's significantly easier than it will be presenting. And that is our final analytic tool. Actually, before we do what I'm about to do, let's do one more little piece of note before we jump into this. And that is going to be our definition for the squeeze theorem, which you'll see in this video is also referred to as the sandwich theorem. Whichever way you prefer is fine. I've always heard of the squeeze theorem, but it's a fairly specific kind of set, but it allows us to deal with functions like what we're seeing up here, which we can't really approach algebraically. We can't do direct substitution. We don't have like the tools beyond like graphing things in order to figure out really what's going on here. We have to instead either rely on the table or bring in something new. This is the something new that in theory we could bring in. Okay, so let's assume that we have some kind of function or a set of functions that are essentially arranged like the Russian nesting dolls. So we'll say that f of x is always less than or equal to g of x, which is always less than or equal to h of x for values of x that live on some kind of interval, we'll say a to b. The squeeze theorem says something fairly mundane that we are then going to use to do something very, very cool. So the squeeze theorem essentially says that we take the limit of everything. So if this is true, then it should also be true that the limit as x approaches c of f of x should be less than or equal to the limit as x approaches c of g of x should also be less than or equal to the limit as x approaches c of h of x. Not particularly remarkable, right? Like that makes a lot of sense. Okay, yeah, if one function is always above and the other function is always in the middle and one function is always below, you would expect that the limits would fall in this order of above, middle, below as well. Sure. The cool thing, though, is that we can use this to make some kind of inference about G. So this is the actual like squeeze theorem itself. But here's the use case. Here's where this is actually like a cool tool that we can use, which is that if the limit of my smallest function matches the limit of my largest function, which we will call some kind of value of L, then what does that tell me about the middle function? It also has to be L. That's why it's called the squeeze theorem. It's like trying to squeeze between two values where there is no space. The only way to do that is to thread the needle perfectly, is to match exactly. So if our top function matches perfectly with our bottom function, then the middle function must also match. And I will say this is for a C that lives on this interval, sure. For B, for part B. Yeah, question 3, part B.
It should just be. Oh, it's part.
Yeah. That should be x over sine of x. So in the condition, instead of x, it should be x over sine of x. Okay. So what does the squeeze theorem tell us? Well, we have this set of essentially nesting doll functions that where one is always smaller than the other, one is always in the middle, one is always larger. Squeeze theorem would tell us that we get to take the limit of each of them for any value of x on this interval. So the limit as x approaches 0 of negative x squared plus 1 should be less than or equal to the limit as x approaches 0 of x over sine of x should be less than or equal to the limit as x approaches 0 of x squared plus 1. That's just what the squeeze theorem is saying. The middle one is the one we care about, what we're trying to answer. What is true about negative x squared plus 1? Does this run into any domain issues around 0? No, it does not. And so what does direct substitution allow us to do? We can just plug it in. Plugging in 0 for x, I get 1 is less than or equal to the limit that we care about. And then on my right-hand side, does x squared plus 1 run into any domain issues? No, it does not. And so what do I get to do? Plug in 0. And so I get that this limit must fall between 1 or 1. And so if it must both be greater than or equal to 1 and also less than or equal to 1, what must be true about this particular limit? It must be 1. Not necessarily. In this case, it was because we were basically working with the same function. Right, we were working with the reciprocal and the reciprocal of 1. But another tool that is a little bit specific in like the information that you would need in order to actually make it work. But overall, is a pretty solid one for dealing with these kinds of issues. All right, questions with squeeze theorem, questions with our kind of analytic ways to deal with our functions here. Right. Cool. So tomorrow you guys can have a lot of time to work on your classwork. I think I'm going to stretch this out a little bit more. So I think we're probably gonna pick up with continuity. We might start it tomorrow, but I'm also honestly fine if we don't get to it until Wednesday. Which would push everything back a day, but we'll just play it by ear. Don't forget the Pearson. In theory, you should be able to do most of it now. I think like 1 through 13 is like up through squeeze theorem, and I think there's only one squeeze theorem example, so it should hopefully be relatively straightforward. Fantastic.
Looks like